to speak here. The discovery of biologically active small molecules, of course, is an enduring theme in both medicinal chemistry and in chemical biology. And I guess I was a bit deliberately provocative with my title here. What I really want to talk about today is how can we explore chemical space in order to identify biologically active compounds quickly, and hopefully really distinctive starting points for discovery programs. So perhaps it's timely to start by reflecting on the diversity of chemical space. And around 10 years ago, the scaffold diversity of the entire organic chemistry universe was analysed. So at the time, there were 25 million cyclic compounds, which it turns out are based on 2.5 million frameworks. Now, of course, there's more than one way to define a framework. In this context, I'm talking about the ring systems and the bits that link the ring systems together. So for this famous natural product, the corresponding framework would be that. Now, of course, if chemists had explored chemical space in an even and systematic way, then we'd have 10 compounds for each framework. And I guess it comes as no surprise that actually the distribution is rather uneven. We don't have a straight line across the middle of the graph. But actually it's remarkably uneven. So the distribution's something like this. One stat is that actually 1/6 of all compounds that have ever been patented or published since the year dot are based on just 30 frameworks, so 30 out of the 2.5 million frameworks. And what that means actually is that 1.3 million frameworks, and more than half of them, have actually only been represented as in a single compound that's ever been prepared. So we've been very interested in approaches that allow you to vary framework combinatorially in order to identify new biologically relevant chemical space. It's probably also worth reflecting on why we've had such an uneven exploration of chemical space. And one reason is that actually the toolkit within medicinal chemistry, the reaction toolkit, is remarkably narrow. So a few years ago, people analysed a whole year of Journal of Medicinal Chemistry and categorised all of the reactions that were reported in that year. And you can see that it's dominated by these 9 reaction classes. So that's bad enough, but if you look into the detail here, it's even worse actually, because 3 of these classes are just deprotection reactions. They don't actually do anything productive at all. So we overwhelmingly focus on reactions that allow us to functionalize nitrogen in particular. There's 1 oxygen substitution down here as well, but only 1 carbon-carbon bond-forming reaction in this top 9. In fact, that's the most recent addition to the Medicinal Chemist Toolkit, but even so, that's now more than 30 years old. So, why is this? Why in an era of unprecedented invention in synthetic chemistry are we simply not harnessing any of these methods at all? Actually, AstraZeneca followed up on this a year or 2 ago, and the title of their paper is very provocative, I would say, in that it says, "Where have all the new reactions gone? We simply don't use them in discovery." Now, today I'm going to use a slightly cheesy analogy, and that's just that searching through chemical space is broadly analogous to searching through physical space. And actually, our exploration of chemical space is far, far more focused than the population density within the island of Great Britain. But you kind of get the picture. If you ask people to look at the square metre of land that they woke up in the morning, maybe, that might be okay for finding the oldest house, but wouldn't be so good if you wanted to find the peaks of activity, so the highest points within the island. So there's 2 problems here. First, we explore chemical space unevenly, and secondly, how do we know that we're actually looking in the right places at all? So we could be having a perfectly pleasant time looking around places like this, kidding ourselves that we're somewhere near a peak of activity. We could be really stupid and go somewhere like here, and then not only would we be looking in the wrong place, but the chemical space would be very ugly and inappropriate for drug discovery. You could trespass in my garden and see some hills on the horizon, but what you really need to be, of course, is up on the ridges in the Highlands of Scotland. So I'm going to talk about 3 approaches. I'm actually only going to very briefly allude to this approach that we had published some time ago, in which we prepared over 80 natural product like molecular scaffolds. I'm going to show how that developed into lead-oriented synthesis, where we try to control molecular properties while still being able to explore multiple frameworks. And then I'm going to take you through a new approach that we've been developing, the subject of my fellowship actually, which we call activity-directed synthesis. And you'll see that this is rather different to conventional discovery workflows. Okay, so here's the approach that we published some time ago, where we took very simple building blocks, so unsaturated building blocks, and then used a small number of highly reliable reactions to stitch them together. And that included a metathesis reaction, which then reprogrammed the scaffold of the molecule. And the idea was that by varying the building blocks that you use and the linkages that you've got between them, it is possible to combinatorially vary molecular framework. And so here are some of the examples of the molecules that we prepared. We think that they have some natural product-like features. So, for example, we've got 1,3,5 oxygenation there. We've got isolated, fused, macrocyclic ring systems, for example. And I guess if we kind of take stock of this and other diversity-oriented approaches, then the molecular diversity, particularly the scaffold diversity, is high. We've done absolutely nothing to control the molecular properties, so perhaps we need to think about that if we're interested in specific discovery applications. But we still need this highly reliable reaction toolkit. And okay, the reactions have changed, but we're still reliant on having highly robust reactions supporting our discovery. Now, one challenge here, of course, is to maintain diversity whilst ensuring that the properties that you prepare lie in the region of chemical space that you're actually interested in. And in the context of drug discovery, we want to start with lead-like molecules, which have perhaps got molecular weight up to, well, 350 or 400, depending on your specific guidelines. We want to control log P, so perhaps we don't want to go higher than about 3 at this stage. And the reason for that is that during optimization, you almost inevitably move to more complex molecules, larger molecules, and more lipophilic molecules. And if you start too big, then you will inevitably end up, or almost inevitably end up, in the wrong place. Now, of course, you can take that to extremes and do fragment-based drug discovery, but again, you would also need to control your molecular properties there. Now, another reason for controlling molecular size, of course, is that it means that your search through chemical space is much easier. And one reason for that is that for each heavy atom that you add, there's an order of magnitude, more or less, molecules that you can prepare. So if you add 6 heavy atoms, you've suddenly made your search 1,000,000 times harder. So for 2 reasons, it's good to control your molecular properties. Now, here's one approach that we published very recently, and I hope you're as pleased as I was with the page number that we ended up with there. Here we were working with Takeda, and they were interested in CNS lead-like molecular scaffolds. So actually the molecular properties required there are a bit different to other fields of drug discovery, and the molecules tend to be smaller, for example. But anyway, we wanted to prepare a large number of scaffolds which might be good scaffolds for CNS lead-like compounds. And it's a kind of bottom-up approach, so it's kind of using the build-couple-pair approach that was popularized by Stuart Schreiber. And the idea is that you have some flexible intermediate here, which has got a number of different functional groups which can be paired together to make rings. So we've got the alkene, the nitrogen, the ketone, and the enolizable position on the left-hand side there. And it turns out that you can pair these together in a number of different ways. So, for example, if you link together the green blob and the yellow blob, then you inevitably end up with a spirocyclic compound. But you can vary quite widely the size and substitution of the new ring that you've prepared. If you link together the blue functional group, the ketone, with either the amine or the alkene, then you end up with a fused ring system. because of course now you've got this bond in both of the rings that are there, and you can do that in a number of different ways to introduce 5- and 6-membered rings, for example. And then actually using some chemistry which one of Joe's former colleagues developed, you can make bridged ring systems. So here doing intramolecular manic chemistry, linking together the green and the beige kind of blob over here, gives you now bridged ring systems in the products. So this is quite a nice toolkit of reactions that allows you to vary the size and substitution of the new ring that you've made. But of course, the other trick that you can prepare is simply to vary the ring that you start with in your starting material. And it turns out that works quite well. So we prioritized 5 of these reactions that were rather high yielding and selective in different senses. And that enabled us now to vary the existing ring too. So for example, we can have a piperidine, we can have this lactam, we can have a 5-membered ring there, a benzo-fused ring, all these other scaffolds down at the bottom. And I guess the reason I like this approach is that it's more modular than any other that we've developed. You've got a toolkit of reactions that really work rather well with quite a wide range of different substrates, which means that you can vary independently both your existing and your new ring. So we prepared around 30 molecular scaffolds, and we did an analysis of compounds that you can make from those to demonstrate that they broadly lay within the right areas of chemical space to provide high quality leads for CNS discovery. So that's kind of a bottom-up approach where you start with building blocks. But we've recently, with Steve Marsden, one of my colleagues at Leeds, developed a kind of complementary approach which we call a top-down approach. So the idea here is that you start by making something that's rather complex. So we actually do this 5+2 cycloaddition chemistry in order to make complex intermediates of this type. And the idea here, I guess, is to imagine that this is a bit like a block of stone, and then you sculpt away at it and end up with different statues or different scaffolds in this case. And there's a number of different kind of broad tricks that you can play. So, for example, you can add on new rings. You can do a ring expansion. So perhaps you could imagine expanding this from a 3-atom bridge up to a 4-atom bridge. And perhaps most powerfully, you can imagine cleaving different bonds within the intermediate. So, for example, if you were to cleave this bond here, then of course you would be left with a spirocyclic ring system, this ring and that ring, in which you've got that as a common atom. So you'd get through to this compound well. And it turns out that these tricks work quite well. So if you start with 4, we actually had 4 intermediates of this general type in the middle here, we were able to make 30 different scaffolds. The ones in blue are ones where we've added on a new ring. The purple ones are an example of a ring expansion. And then I particularly like the bond cleavage approach, because these 3 scaffolds here in red actually all came from the same starting material, and it just depends which bond you cleave. Their topologies are rather different. So I've already talked about cleaving this bond here, but you can break this CX bond there to give a 5-7 ring fusion. You can break this bridge here to get a 5-5 ring fusion, for example. Now, that's all very well, but actually we've done absolutely nothing to demonstrate biological relevance. And the way that we decided to do this was to construct a fragment set based on these scaffolds. Now, we're not particularly interested in doing fragment-based discovery, at least not within this project here. Our objective here really was just to demonstrate biological relevance. And of course, because searching through chemical space is easier if you've got smaller compounds, we thought that a fragment-based approach might be a reasonable way to do that. Now, fragments tend to have rather limited shape diversity. And in fact, there was a consortium, the 3D Fragments Consortium, some members of that consortium here. And the raison d'etre of that consortium was to address the limited shape diversity of fragments. Most commercial sets tend to be very much dominated by flat molecules that lie along this edge of the PMI plot. That tends to mean that you've got rather limited opportunities for exploring new vectors around fragment hits that you might find. To show you the kind of fragments we prepared, they were rather more three-dimensional. They extend much further out into the three-dimensional regions of the plot. And to give you a feel for the kind of molecules we've got in mind here, I've just given you some examples there. Our fragments are actually rather natural product-like. One way to capture that is using this natural product-like likeness score which has been developed. Compounds with a positive score tend to be natural product-like, whereas synthetic compounds, commercial fragment sets, tend to have more negative scores. And the red distribution here is the distribution of our fragments, and you can see they're shifted towards the right-hand side. Now, although those fragments are natural product-like, they've got broad structural features reminiscent of those found in natural products, actually the specific frameworks are not found in natural products. So one way of analysing that is to use a scaffold tree, something like this. So the scaffolds that we prepared around the outer ring of this diagram here, and actually also the boxed ones there as well. And what you do is you systematically remove one ring at a time until you end up with the most important ring system. And there's a set of rules that can allow you to do that. So you can see we've got the monocyclic ring systems down here. Now, the colour here is illustrating whether or not the frameworks are found within natural products. So all of the green ones are not found in natural products at all. And you actually have to simplify our frameworks quite a lot before you get to ring systems that are found in natural products. So generally with either just one or two rings. So all bar one of our synthetic frameworks are not found in natural products. This is the only one which it turns out is found in 14 different natural products. So it's rather like adding an additional branch to the scaffold tree. So here are the branches which are represented within natural products, the natural product frameworks out at the leaves, and then the most important ring systems, your kind of trunk. And what we've done is to add in an additional branch to the tree. They're kind of distant cousins of the natural product-like frameworks. And these are natural product-like. They've got broad structural features reminiscent of natural products, but they're not actually found within natural products. And I guess the question is, are these sensible starting places for discovery? Now, in order to probe that, we collaborated with Frank von Delft at the Structural Genomics Consortium and Diamond. He's got a very nice facility at Diamond which enables you to do high throughput fragment screening using crystallography. So you grow your protein crystals, you soak each one with a fragment, you pick your crystals, do X-ray diffraction, and then fit your data. And you can screen of the order of 100 fragments or so in the course of a day. So we screened against a wide range of different targets. We're going to hear more about bromodomains later on, I think. And in each case, we found a fragment hit. So I'm actually going to focus on this particular bromodomain compound here. So these are a class of proteins that recognize acetylated lysine residues. So this is how they do it. Here's a fragment with the side chain of acetylated lysine soaked into it. And you can see that there's this network of hydrogen bonds down here that allow the acetylated residue to be recognized. And it turns out that our fragments bind in the same binding site and use a very similar kind of interaction network. So we have different acetylated or acetyl mimics, so these expanded versions down here, but still interacting with this asparagine, tyrosine, and then through water down there. But what we're doing now is to pick up additional interactions elsewhere within the pocket. So, for example, through water to these residues here, or in the case of these two fragments, we've got now a heterocycle fused on there. We're picking up different interactions elsewhere within the pocket. And these hits are completely different to those which were found using a conventional flat fragment set, which don't tend to pick up these additional interactions. So we think that this provides some evidence that the kind of novel frameworks that we've been able to prepare with this route are biologically relevant. So in other words, frameworks distantly related to natural product frameworks are also biologically relevant and can provide distinctive starting points for discovery. So with lead-oriented synthesis then, we've still got high diversity. We can still make many different scaffolds, but now we do it whilst controlling molecular properties, thinking about making compounds that lie within the region of chemical space that we want to search in. But we still need this highly reliable toolkit. And I guess the thing that most frustrated us is that if you were to use these kind of synthetic approaches in a discovery program, you would still need to use a conventional medicinal chemistry workflow where you design, make, purify, test a set of compounds, and in doing so expend a roughly equal resource in all of the compounds that you consider. So that takes us on nicely to our new approach, which we call activity-directed synthesis, which you'll see now focuses the resource in the active compounds. So this is a bit like focusing your search of chemical space. It's a bit like a big cloud descending over the island of Great Britain, just leaving the peaks of activity peeking through. So what we wanted to do really was to take some inspiration from the way that natural products arise. So of course they arise through biosynthetic pathways, where we have metabolites, which are substrates for biosynthetic enzymes, which together with cofactors lead to the production of constellations of natural products. Now, of course, this approach doesn't involve design. These structures arise in a way that's structure blind and driven by function. These natural products persist because they provide a benefit to the host organism. And in the form of evolution, there's a mechanism for optimization of the pathway to lead to the optimal distribution of natural products. And we wondered whether it was possible to draw inspiration from this. So what we would have would be substrates, which would be broadly analogous to our metabolites, and we'd have catalysts, this time chemical catalysts, and we would deliberately design reactions which had many possible outcomes. So I've put up some possible outcomes from palladium catalyzed reactions of the substrates shown there. There's a number of products that you could conceivably imagine being formed. And the idea would be to then screen those directly and identify those reactions that give active products. And it'd be nice if we could do this in a way where there was some kind of evolutionary feedback in order to optimize the route. And that way you'd be not only discovering a bioactive compound, but you'd also be discovering a parallel route which allows you to make it at the same time. Okay, so that's kind of the idea on paper. So in order to demonstrate it or prove the concept, we decided to find some ligands for androgen receptor. And to give ourselves a leg up, we recognise that this fragment is found within many ligands for androgen receptor. And as a medicinal chemist, you might imagine growing this fragment in a number of different ways. So you could imagine adding on a new ring, biting back onto the existing ring, growing out to a new functional group, or perhaps doing something really wacky. Well, actually, I suspect you probably wouldn't do that because it would be too risky. So what you would need to do in order to investigate these hypotheses then would be to design a set of compounds for each of the hypotheses, maybe 30, something like that, make and purify those compounds and then test them. And what you would find probably is that some of the hypotheses were good and some of them were less than good. And you would, the key with activity-directed synthesis is that it's possible to explore all of these at the same time. So in order to do that, you need some promiscuous chemistry. And we were very much drawn to metal-catalyzed carbenoid chemistry. So you can see that each of the substrates in black contains the fragment, contains a diazo group, which will lead to the formation of a metal carbenoid, and it's got a side chain which can perhaps react with that metal carbenoid. And the nice thing about this chemistry is that there's many possible outcomes. So we can have both inter- and intramolecular reaction modes. We can do CH insertion, so perhaps into this CH here. We can do metathesis and cyclopropanation, or we can do ylid formation and rearrangement. So the key here is that the substrates look rather similar, but the products, or my hypothetical products here, look rather different. So we're able to explore diverse chemical space with this common tool within our activity-directed synthesis toolkit. So how does the experiment work? Well, you start by setting up your reactions in array format. So your inputs are substrates, co-substrates, catalysts, and solvents, and you vary those inputs. You let your reactions go to completion. You scavenge the catalyst using a scavenging resin, and then evaporate down the crude reaction mixtures, dissolve them in DMSO and then in buffer, and then assay them for biological function. So that way you find out which of those reactions gave rise to an active product. You've no idea what that product is, but you know how you made it. What you can then do is to design another reaction array based on the data that you find. So you might imagine in the second round, now exploring combinations of substrate, co-substrate, catalyst, and solvent, which are similar to the hit reactions that you found in the previous round. And a trick you can play here is to simply assay at lower concentration in successive rounds in order to raise the threshold for biological function. Now, at some point, you're going to run out of time, resource, patience, or whatever, and you perhaps want to know what you've actually discovered. So that's easily done because, of course, you know how you made all of those active products. So what we typically do is to scale the reactions up by a factor of 50, purify the products, work out what their structures are, and demonstrate for the first time that the isolated compounds do indeed have the required biological function. So this is all hypothetical. How does it all work in practice? Well, here George designed an array of just 36 reactions to start with. There were 12 substrates and 3 catalysts. And what he found was that some of the substrates do not give rise to active compounds with any catalyst. But in other cases, if you use the right combination of catalyst and substrate, you give rise to an active product mixture. So the 4 green substrates there are shown here. And he decided to take these on into the next array, and actually took these 2 on as well to demonstrate that they don't lead to productive reactions subsequently. So now we've got 6 substrates in the second reaction array, and we used a wider range of both catalysts and solvents this time. So each substrate is now undergoing 32 different reactions with these combinations of catalyst and solvent. One of my favourites is substrate 3, actually. So under most conditions, it does not give rise to active products. It gets steered towards inactive products. But if you use either the green or the black catalyst, then the reaction gets steered towards an active product. We don't know what it is yet, but it gets steered towards an active product. And you'll see that substrates 11 and 12 didn't go anywhere. So we now designed a third reaction array based on substrates 1 and 3 and 4 new substrates which were structurally related, and now really focusing on the promising types of catalysts and solvents. They were rhodium carboxylate catalysts in this case. So finally, there were 108 reactions in the third round. We assayed at 10-fold lower concentration once more, and that allowed us to identify some reactions that were worth scaling up. So what do we find? Well, here's one example. The reason I've drawn this out is that we would have never rationally chosen to use this catalyst. It was developed by Justin Dubois, and it's a dicarboxylate which bridges across the dirhodium catalyst. But nonetheless, it's by far the best for giving the active compound. So it actually leads to a CH insertion here, and therefore the formation of this beta lactam. And we'll talk about yield later on, but it's formed in good yield. Once we'd worked out the structure of the compound, we then characterized it and showed that it was indeed a submicromolar agonist of the androgen receptor. Now, if you were feeling really skeptical, I guess, you might say, well, maybe the activity comes from residual metal or something. So we made it via a rhodium-independent route and demonstrated that it is indeed the active component. It's also instructive to look at some of the chemotypes that you explored, but that weren't prioritized. So here's a reaction from round 1, which kind of gave borderline activity. There were actually 3 products formed. So 2 products of CH insertion into an aryl CH, so these 2 here, but also a cyclopropanation product as well. The borderline activity comes from the cyclopropane. So these are chemotypes which we're exploring, but not prioritizing because they aren't as good as those formed in the best reactions. So what chemotypes did we find? Well, you've seen the beta-lactam before. We found another beta-lactam structure related and a gamma-lactam as well, where we've done a CH insertion 1 further along the chain. All 3 products are produced in good yield. All of them are submicromolar ligands of the androgen receptor. This is the bit that I think George was most pleased about. So in total, he prepared 16 substrates, did 336 micro reactions, but only 3 columns, or only purified 3 compounds, the 3 active compounds that you see here. So you really are focusing your attention on the relevant parts of chemical space to your specific target. So how did these syntheses evolve? Well, the active compound was produced in round 1, otherwise we wouldn't have taken that reaction forward. But we then used a wider range of catalysts and solvents in round 2, which increased the yield of that product. So you naturally prioritize those reactions that give the highest yield of your bioactive compound. We introduced a new substrate for round 3, and that allowed us to hop to a related chemotype as well. Now, George was still a bit frustrated, and that was that he still had to prepare all those substrates. Now, we can actually now do it in a single step, but we couldn't at the time. There were 3-step syntheses of each. So what he thought would be nice would be, why not start with a fewer number of substrates, but now do intermolecular reactions? So now you can buy things to react them with from your favorite compound vendor. So he took forward these 2 substrates now, or these 4 actually, because we've got either hydrogen or acetyl in that position there. And he now reacted them with something else, so co-substrates, these shown in blue, and you can see that these were chosen for their diverse potential reactivity. You can imagine cyclopropanation, CH insertion, NH insertion, ylide formation and rearrangement, insertion alpha to nitrogen or oxygen. Lots of different outcomes might be possible. Now, one challenge, of course, is that you now have a combinatorial explosion in the number of possibilities. So to keep tabs on numbers, he did a randomly chosen 192 reactions from the 480 possibilities. And I think he got quite lucky, because actually only 2 of those 192 reactions give an active product. So it's both from the same substrate with either the co-substrate in this column or the co-substrate in this column. You get your first hint that it must be an intermolecular reaction, because if you don't have a co-substrate, you don't get any activity. So what were the co-substrates? Well, it was this diazo, sorry, in black, with either indole or cyclohexene as the co-substrate. So on the basis of that, he took forward this diazo and one other into the next round, and chose 18 new co-substrates which were structurally related to these. And you can imagine what you might do. You might vary the ring size, introduce heteroatoms, that kind of thing. So in the next round, he did just 86 reactions and actually now got hits from both of the substrates this time. He prioritized those from this substrate here, so it's the one you saw earlier, and now you can see that they come from reactions with different co-substrates. So we designed another array based on that. So in the final array, we just took forward 1 diazo, 12 structurally related co-substrates to those, and 4 different catalysts, but now just in the best solvent. And then we assay at 5-fold lower concentration, and we prioritize the most interesting reactions. Okay, so some things to point out here. So this co-substrate here gives rise to active products, but you get different activity depending on which catalyst you use, presumably because the yield of the active compound is just better with the red catalyst. The final column is perhaps a little bit more interesting. So now if you use an R-configured catalyst, you get activity, but an S-configured catalyst doesn't give you activity. So that probably must mean, I think, that the product must be chiral, the reaction must be enantioselective, and the two enantiomers must have different activity. So that's probably what's going on there. So at this point, we worked out what the compounds were. So let's look at how the activity-directed syntheses evolved. So in round one, you'll remember it was either cyclohexene or indole, and these led to the formation of these products by either a cyclopropanation or by a CH insertion. These are quite dull, particularly this one, because you can buy that carboxylic acid. You could have prepared that in a conventional medchem program. In the next round, we find that adding heteroatoms into some positions improves activity, as well as fusion of an aromatic ring. And then in the third round, our co-substrates, our promising co-substrates were these. And actually, unexpected things happened here, things that we wouldn't have we wouldn't have predicted, I wouldn't say. So you can see perhaps why we chose to use this co-substrate, because dihydropyran had been good in the previous round, but it turns out it no longer does a cyclopropanation. I should explain that we use a 10-fold excess of the co-substrates. This is actually a kinetic resolution. And with the R-configured catalyst, we give rise to this product here. So we get selective reaction of one of the enantiomers to give this product by OH insertion. The reason why if you use the other enantiomer you don't see activity is that the other enantiomer is about 6-fold or so less active, and we were assaying in between those two values there. So this was interesting, particularly because this reaction isn't known. So we think that this was the first example of a new asymmetric reaction which had been discovered on the basis of the biological activity of the product, not by design or anything like that. So what's going on with this final co-substrate here? So you might guess that it would do a cyclopropanation, but it doesn't. In fact, we now get reaction of the nitrile over here. So we weren't expecting this, but that's largely due to our ignorance than anything else. This is a known reaction developed by Chris Moody at Nottingham, where you react with a nitrile to give rise to an oxazole. So here's the product of that reaction there. And I guess this is quite a common trick that medicinal chemists use to conformationally constrain an amide, so in a kind of isosteer, which retains the hydrogen bonding capacity in some sense of the group. So I think what we found here were 4 different classes, I think. So this kind of class up here, the cyclopropanes are all clearly structurally related, but then these two are rather different. And again, they've all been discovered with the same workflow, and this time he prepared just 4 substrates, bought everything else, over 300 reactions, and we identify the 7 active compounds and purify and characterize those compounds there. Again, really focusing our attention on the interesting reactions that give rise to active products. So in contrast to diversity and lead-oriented synthesis, activity-directed synthesis is a bit different. It's structure-blind and function-driven. So I think that the diversity is retained. We now deliberately use promiscuous reactions that can explore broad swathes of chemical space. We can still control our molecular properties because, of course, we can decide what we're going to react together and make sure that we don't have the possibility of products that are too big or too lipophilic, that kind of thing. We now want, ideally, promiscuous reactions rather than the kind of highly reliable reactions that we typically require within discovery workflows. And I think the thing that we're most pleased about is that now all of our energies are expended on the bioactive compounds rather than having to treat each compound the same, irrespective of whether it turns out to be of interest. So I'd like to finish by thanking my group. So here on a day out in beautiful Home Valley in West Yorkshire, I'd like to thank the people who did this work. So Joan did all of the bottom-up stuff from the building blocks to give the CNS lead-like scaffolds. The top-down stuff, so where we were cleaving rings, that kind of thing, that was done by the team shown in red. all of the activity-directed synthesis was done by a single PhD student, so by a highly talented student, but nonetheless, I think this shows you the efficiency of the workflow as well. I really want to thank our collaborators without whom none of this would have been possible. So in chemistry and structural biology and in medicinal chemistry within industry. I'd like to thank these bodies for funding our research and of course you for your attention. Thank you.